A lot of modern technology is very clever indeed, but often we find that nature got there first. Like bone, it's really nature's fiberglass. Why? Well, if you look at fiberglass, like this case, it's actually made with fibers of glass, long thin fibers of glass, embedded in plastic. And that plastic starts as two liquids, you put them together, and the molecules in them get longer and longer and longer. It goes stiffer and harder until it sets like a hard plastic, well, as a hard plastic. So now we've got fibers of glass in a hard plastic. So we get the hardness and rigidity of the plastic, but the flexibility and the toughness of the glass fibers. And that's a great combination. And that's what you have in bone. If you take bones like these, chicken bones and chop bones, they've got a hard matrix, which is mineral salts, largely calcium phosphate with some carbonate there. And the fibers running through it are a protein called collagen. And the two are really working together to give you a bone that's hard, flexible, tough, really remarkable stuff. Now it's hard to deconstruct fiberglass and get those two elements out, but you can with bone. So if you take bones like these and put them on the glowing coals of an old fire and let it all die down, you can then take them out and they'll look like this. They still look like bone. They're quite recognizable. But if you test them for their hardness, you'll find that they snap and they crumble. They're really completely useless as support mechanisms. They're just sort of ash, really, because all the collagen fibers have been burnt out of them. You're just left with the minerals. But you can do the reverse. You can take the minerals out and leave the collagen fibers, and for that you need an acid. And the acid everyone has at home is vinegar. It's acetic acid. So let's pour a generous jar full of that. Now inside that you've got acetate ions and hydrogen ions, but it's not quite enough for what we want. If you take table salt, sodium chloride, and stir in a couple of teaspoonfuls of that and dissolve it up, you've got something interesting going on in there. You've now got the acetate ions and the hydrogen ions, but you've also got sodium ions and chloride ions. And the hydrogen ions and the chloride ions make hydrochloric acid. That's a lot stronger. And into that, you take your bones, plonk them in, and you leave them with the lid on for, well, I would say 2 or 3 weeks. Test them at intervals. Change the vinegar if you want to. What comes out at the other end is this. They still look like bone, but if you test their rigidity, it's all gone. This one's a bit like leather and sort of crushable, whereas this one is really quite horrible. It's gone rubbery. It's a bit distressing to watch. If you imagine that sort of thing inside your leg, it wouldn't be doing too much of a job at all. It's a rubber bone because all the minerals have gone. So that striking combination is what makes bone the wonderful material it is. That's why over the years, the centuries really, it's been used for all sorts of tools, from hammers to knives to oars to fish hooks, all sorts of things that today you might make out of fiberglass. Some of them are a bit bizarre. This one is an ancient Tibetan pageantry trumpet. It's actually a human leg bone. It's hollow and it's hard, and just like fiberglass, it can make a very fine trumpet.